Iodide ions are oxidized to iodine by hydrogen peroxide in acidic conditions. We can see that 1 mole of hydrogen peroxide reacts with 2 moles of protons, which are provided by the acidic conditions, and 2 moles of iodide ions to produce 1 mole of iodine and 2 moles of water. The rate equation for this reaction can be written as rate is equal to K by the concentration of hydrogen peroxide to the power A by the concentration of iodide ions to the power B by the concentration of hydrogen ions to the power C. In an experiment to determine the order with respect to H+, a reaction mixture is made containing H+, with a concentration of 0.5 moles per decimeter cubed. A large excess of both H2O2, so that's the hydrogen peroxide, and iodide ions is used in this reaction mixture so that the rate equation can be simplified to rate is equal to K1 multiplied by the concentration of hydrogen ions to the power of C. Explain why the use of a large excess of hydrogen peroxide and iodide ions means that the rate of reaction at a fixed temperature depends only on the concentration of hydrogen ions. This question is worth 2 marks, which means we can expect to see 2 points we need to make in our answer in order to get those marks. So, to begin with, we need to look at how using a large excess is going to affect the rate equation. And we've seen that it's taken out the concentrations of the hydrogen peroxide and the iodide ions, meaning it's no longer dependent on that. And the reason this is the case is that when we have a large excess of a reactant or a species even in the rate equation, what we will find is that any changes that occur in the concentration of that species becomes negligible because we have such a large excess that it's still going to be an excess. And what this means is that the concentrations for both our hydrogen peroxide and our iodide ions are effectively constant. So while they will still be being used up by our reaction, they have such a large excess that they're still going to be in excess, so that change is irrelevant. And because these concentrations are effectively constant, this means that they have absolutely no effect on the rate of reaction, because they're still in, even when we've used up some of these reactants, they're still in excess. They're not limiting reactants, so they don't have any effect on the rate of reaction anymore, because they are in such a large excess. They're going to remain in excess no matter what really happens to this reaction. So they end up having no effect on the rate because they're in such a large excess. So the 2 points that we really need to get in order to secure those marks is the first saying that the concentrations are effectively constant, and then the second mark comes from saying that means they will have no effect on the rate of reaction. And those are the 2 marks for this question. Samples of the reaction mixture are removed at timed intervals and titrated with alkali to determine the concentration of H+. State and explain what must be done to each sample before it is titrated with alkali. This question is worth 2 marks. So, in order to be able to determine the concentration of the hydrogen ions at a specific time, we need, for the point we take that sample from the reaction, to continue to be representative of that point in the reaction. And if we just take a sample, then we take the sample of all of the reaction mixture, and it can continue to react. So what we need to do, and this point here is our first mark, is that we must stop the reaction, which is often referred to as quenching the reaction. So you must stop the reaction so that it doesn't continue to react and the concentration of our hydrogen ions continues to change. We don't want that. We need it to be specific and staying at the point that we took the sample. So we stop the reaction. There are a few ways we can do this. One way we could do this is we could stop the reaction by cooling the reaction. So we could cool the sample, as we can bring the energy of the reaction down under the activation energy, which would stop it, or maybe not potentially completely stop it, but would slow it enough that the continual rate would be negligible. There are a few other things we could do though. We could also dilute the reaction, so that the changes in concentration become more and more negligible. So by diluting our sample, that's one way we could do it. We could also add a reagent to remove our other reactants. So that would be our hydrogen peroxide and our iodide. However, what we need to be very important about is that we're adding a reagent to remove these. a common way that students might think to stop the reaction is to go, one of our reactants is hydrogen ions, so we can just add alkali to neutralize it, and then there won't be any reaction. The problem is with that, while it would stop the reaction, it also would remove the concentration of hydrogen ions, which is what we're actually trying to measure, and so that would prevent us from actually obtaining any results. But that it gets us to 2 marks to the question. The first is for saying we stop the reaction, and the second is for explaining how we can stop the reaction, where one of these 3 options would get us that second mark. A graph of the results is shown in Figure 1. Figure 1 shows the concentration of hydrogen ions in moles per decimeter cubed against time in seconds. Explain how the graph shows that the order with respect to hydrogen ions is 0. This question is worth 2 marks, so there'll be 2 points that we need to get in our answer in order to get the full marks of the question. So the key thing to note about this graph, first of all, is that the gradient is going to be constant. We have a straight line on the graph. So our first point here is going to be that the gradient is constant. And the importance of this comes from what that gradient is actually equal to. If we look at our graph, we can see on the y-axis we have concentration, on the x-axis we have time. Now gradient is y over x. This means we've got concentration over time, and concentration over time is equal to the rate of reaction. So the gradient is constant. So because this gradient is constant and it's equal to the rate of reaction, this means that the rate of reaction is also constant. And the reason this is important is that throughout this graph, the value of concentration of hydrogen ions is changing. So this rate of reaction is also constant as our concentration of hydrogen ions, that's the square brackets H plus, is as this changes. And this means that it's going to be order with respect to this of 0, because it's clearly having no effect on the rate of reaction, because it's changing, as we can see as it's going right up and down the y-axis, as the data shows, but this throughout all of this, the rate of reaction is constant. So that's all we need for the question, and our 2 marks from this come from pointing out that the gradient is constant and showing essentially the observation from the graph that the rate is going to be constant, so talking about the gradient. And then secondly, it's coming from pointing out that this is happening as the concentration is changing, which then shows that it's going to be order 0 when it comes to the concentration of hydrogen ions. And that's the 2 points we need for that question. Use the graph in Figure 1 to calculate the value of K1. Give the units of K1. This question is worth 3 marks, so we are going to get 2 of those marks from calculating and giving the value of K1, and the third from giving the units of K1. So to begin with, we need to actually look at and work out how we're going to give the value of K1. So we were given previously that the rate is equal to K1 multiplied by the concentration of hydrogen ions to the power of C. However, we have just shown that C is equal to 0. So therefore, the rate is going to be equal just to K1, as we showed that the concentration of hydrogen ions did not affect the rate of reaction. So all we need to do in order to find the value of K1 is just simply find the rate of reaction, which we can do by using the graph in K1, as it's going to be equal to the gradient, which we can see here. So the gradient is equal to concentration over time, which is equal to our rate of reaction. So all we need to do is find the gradient, which we can do by changing y over changing x. So if we look at the numbers present, we can see that first of all, the change across the entirety of the graph for our y-axis, our concentration, is 0.5. And then secondly, we can see that the change along the x-axis for our time, it ends up here between what would be 410 and 420. So that's going to be 415 there. So that gets us 415. And that is going to get us a value of 1.2 times 10 to the minus 3. So there is a value of our gradient. So what we are then able to do is take this back and put in this value. So we have 1.2 times 10 to the minus 3 as our value of as the value of K1. Something to note is that even though on this graph this is a negative gradient because this is going downwards. It will be a negative change in concentration. We don't have negative rates of reaction, so we essentially ignore the fact that we have this negative sign there. As the rate of reaction it's not a vector quantity, it's scalar, it only has the size of it, it's not direction at all. So that's the value of the rate of reaction. However, we do need to, the value of K1, however, we do need to give its units. So because, as we can see here, the K1 is just equal to rate of reaction, that means it's going to share its units with the rate of reaction as well, which means it's going to be the same units as the rate of reaction. So those units are going to be equivalent to concentration over time. So the unit of concentration is moles per decimeter cubed, and the unit of time is seconds, so that's per second. So our units are moles per decimeter cubed per second. And that gets us our 3 marks. We get 2 for our value of K1, which we can 1 for the actual value and 1 for how we've worked it out, and then that third and final mark comes from giving the units. A second reaction mixture is made at the same temperature. The initial concentrations of hydrogen ions and iodide ions in this mixture are both 0.5 moles per decimeter cubed. There is a large excess of hydrogen peroxide. In this reaction mixture, the rate depends only on the concentration of iodide ions. The results are shown in Table 1. Plot these results on the grid in Figure 2. The first 3 points have been plotted. This question is worth 1 mark, so we need to plot all of these points correctly. So these 3 have already been plotted, but all of these remaining 5 here in order to get that 1 mark. So scrolling down to view the table, we can see that our first 3 points have been plotted along here, and so we need to start with these ones. So to begin with, we've got 400 and 0.31, so we have 400 here, 0.3 is there, and we can see that as there are 10 small squares between over a gap of 0.1, we have 0.01 being one of the small squares. So that means that our first point is going to be here. Then we have 600, 0.24, so 600's here, 0.2's here, so 1, 2, 3, 4 gets us our next point, like so. Then we have our third point is 800 and 0.19, so we have 800 here, we have 0.2 here, so down 1 from there gets us to 0.19, so there is point number 3. Then we have our fourth point is 1000 and 0.15, so 1000 is here, and 0.15 is this line here, so there is our next point. And our final point is 1200 and 0.12, so 1200 is the end here, and then 0.12 is 1, 2 up from our 0.1 line there. So those are the 5 points we need to plot on the graph. If we've now that we've plotted all 5 correctly, that's all we need for the 1 mark. Draw a line of best fit on the grid in Figure 2. This question is worth 1 mark, so all we need to do is draw that line of best fit, and that will get us a mark for the question. So to draw said line of best fit, all we need to do is start at our first point here, and then draw a smooth curved line that passes through all of our points in a nice smooth curve, like so. It needs to be a nice smooth curve rather than a series of straight lines connecting all the points. So as long as we have drawn a curved line that passes through our points, then that will get us the 1 mark, but we would not get the mark if instead we were to do a series of straight lines connecting each point. It needs to be a curved line. Calculate the rate of reaction when the concentration of hydrogen ions is equal to 0.35 moles per decimeter cubed. Show your working using a suitable construction of the graph in Figure 2. This question is worth 2 marks. From the wording of the question, we can infer that we're going to get 1 of those marks for the actual value of our rate of reaction, and the other for the suitable construction. So if we look at Figure 2, we can see this. I have already drawn on the suitable construction, as it's referred to as, by including this tangent to the graph at 0.35. Now, the way we're going to find the rate of reaction is by using the gradient of the graph. So we use a tangent when we want to find the gradient at a specific point on the curve, like this. So this tangent gives us 2 points which we can use to start calculating that gradient. If we look here, we can see that the endpoints are 0, 0.46 for this one here, and for this one here, we can see we have 1100 and 0 as our coordinate points. So we can use these two, which we've taken from our suitable construction on the graph, in order to calculate the gradient and therefore the rate of reaction. So what we're going to do is take those points. So the rate is equal to the change in y over change in x in this case, which is equal to 0.46, as that's the total change in y, while on our graph that was a negative change, it was going down. Because we're not going to get a negative rate of reaction, our rate of reaction is always going to be positive, we ignore the negative sign. Then our change in x was 1100, it went from 0 to 1100, so that gives us the calculation, which we can now put into our calculator to get a value of 4.18 times 10 to the minus 4 moles per decimeter cubed per second. So 4.18 times 10 to the minus 4 is our final answer for this graph of this line of best fit. However, the line of best fit for individual graphs will vary slightly. So what this means is that there is a suitable range of answers, which, as long as your answer for your value for the rate of reaction falls within, it will be accepted due to deal with just slight differences in how that graph has been, in how each student has drawn their graph. But that would get us the 2 marks question, one for our actual value and one for showing that we have gained that value in the correct way from the graph by showing that tangent and showing that we're taking the gradient from it. A general equation for a reaction is shown. It shows us that A plus B plus C reacts to form D and E. In aqueous solution, A, B, C, and D are all colourless, but E is dark blue. A reagent, X, is available that reacts rapidly with E. This means that if a small amount of X is included in the initial reaction mixture, it will react with any E produced until all of the X has been used up. Explain, giving brief experimental details, how you could use a series of experiments to determine the order of this reaction with respect to A. In each experiment, you should obtain a measure of the initial rate of reaction. This question is worth 6 marks, so it is a 6-marker question, which means that it's going to require an extended written response, which can be broken down into 3 parts. For a question about an experimental method like so, where we are asked to experimentally determine something, we generally are going to have the following 3 stages. We are going to have the preparation, so everything that we do in terms of the practical procedure before the reaction actually starts. We then have the procedure, which is how we then actually set off the reaction and record what we need from it. And then finally we have our analysis section, which is what we then do with all the data we've recorded from our experiment. So to begin with, we start by talking about the preparation, and with these stages in the 6 marks question, there will always be kind of at least three specific points, sometimes it's more than 3, that we need to hit in order to have fully described that stage. And however, just because they are 3 distinct points doesn't mean that's necessarily going to be 3 sentences. For example, here, this preparation stage can actually be done entirely within 1 sentence for this. So what we need to do for our preparation stage is we just need to begin by measuring everything out. So what we're going to do is we're going to measure known volumes. So all that means is that we have recorded the volumes that have been measured. We don't necessarily have to state exact numbers here, and especially when we have a general equation like this rather than specific compounds, then we're not going to actually be able to know. There won't be any objectively correct suitable values. So simply known volumes allows us to give that in a general sense, like the equation for the reaction is given it. So we measure known volumes of A, B, C, and X into separate containers, and we need to specify that they are in separate containers, as if we place all of these together, at least A, B, and C, they will begin to react, and that sets the reaction off before we have actually started anything else we need to do to measure or record any information from that reaction. So this is the entirety of the preparation stage, and there are three points within here that this 1 sentence is hit that we need to get. The first is that we need to talk about measuring the known volumes of A, B, and C, and the second is measuring a known volume of X. So while these seem to be very similar in the same point, the distinction comes as to why they're 2 separate points from the fact that A, B, and C are our actual reactants in the reaction we're looking at, whereas X is, while it will react, and it is a reactant in a reaction that will occur, it is not one of our main reactants. It's closer to almost an indicator than a reactant here. So that's considered separate. It's a separate point. The third point is that they're in separate containers so that the reaction doesn't begin immediately once we finish measuring everything out. Now, stage number 2 is the procedure, and this is in this sort of question the longest of these stages. The first thing we need to do, however, is actually get the reaction going. So we're going to mix all four of the species together, as we want the X in there as well. And we'll see why in a second. On top of mixing the 4 species together, we're going to start a timer. So the reason we're starting a timer and including X in there is that until as the reaction occurs, it's going to produce E. However, while we've still got X in there, as it's told us, that E is not actually going to produce any visible color change because it will immediately react with the X to form colorless solution. However, after a while, that X will be used up and E will be produced, which will actually produce a color change. So because of this, we can measure the rate of reaction by how long it takes to produce enough E to counteract the X. And because once all the X has been counteracted, the E is being produced and causing a change in color, that provides a visible change that we can time how long that takes in order to give us an idea of how quickly the rate of reaction is going. So that gives us our next step. We're going to record how long it takes for the blue color to appear. Now, there are a few ways of determining when the blue color has appeared in order to make it less objective. Obviously, it can be subjectively done by just looking at the reaction vessel and allowing it to be kind of subjective like that. But you could also use a disappearing cross method or a colorimeter to make it less subjective and determine like a more objective point as to when the blue color has appeared beyond just simply looking at the reaction vessel. So those are the first 2 points in the procedure: mixing the 4 species together and starting a timer, and recording how long it takes for that blue coloring to appear. The third point is really split into multiple points itself, as we've done one experiment, but now we need to repeat the experiment. So we're going to repeat the procedure with different concentrations of A. And we're doing this to allow us to start producing a complete data set and to see how the rate of reaction is going to change with respect to A. So with different concentrations of A. However, we can't just change the concentration of A without controlling other variables. So we're going to use different concentrations of A, but all other concentrations, so that's B, C, and X, must be constant. These are some of our control variables. So in order to ensure that any change we're getting in the rate of reaction is due to that change in A, we must make sure we aren't changing anything else. On top of that, we've got other control variables we need to mention. So the third point is really kind of encompassing all the control variables here. So all other concentrations must be constant, but also all volumes of species, including A's. So we're not changing the volume of A either. We need to we're only changing the concentration, so we only have the one variable which is changing. All volumes must be constant, and there's one final control variable that could affect the rate of reaction that doesn't relate to the reagents themselves, and as in it's not a quantity which belongs to the reagents we're adding. It is instead that the temperature must be constant. Every one of these repeats must take place at the same temperature, as the temperature can affect the rate of reaction. So this could be achieved by by measuring the temperature beginning and checking everything is starting at the same temperature. But for more control, a water bath could be used. So the temperature must be constant as well, and that gives us covers all our points for the procedure here. It starts by explaining the actual experimental procedure, so mixing them together and starting a timer, recording how long it takes for that blue color to appear, and then it talks about the different variables involved, what we're actually going to change, our independent variable, what we're changing. So in this case, it's the concentration of A, and then all our control variables, and making sure to state that they must remain constant. It's important to state this, that you leave your control variables constant, even if you can't assume just because you haven't said you're going to change them that means they're going to stay constant. You need to state they must be constant in order for that to be included in your explanation. You can't leave it just assumed that they stay constant. But that gives us the full procedure we need, and now we have a set of data for the time taken for the blue color to appear against for different concentrations of A. So what we're going to do now is we are going to calculate 1 over that time, so 1 over time, as a measure of the initial rate. So with this form of calculating the rate of reaction, we are only looking at the occurrence of one event rather than like a continual quantity which we're monitoring, like if it's concentration we're monitoring. So instead of doing, say, concentration over time, we just use 1 over the time taken for that event to occur instead. So we use 1 over time as a measure of initial rate. Once we've calculated 1 over time for each of the times for our concentrations, the next thing we're going to do is we're going to plot a graph of logarithm base 10 of 1 over time, so that's on our y-axis, against log base 10 of our concentration of A, like so. And the reason we're using logarithms here is because the relationship with the order in a with respect to our different reactants is an exponential relationship. The order is a power which the concentration has been raised to. So by using logarithms, what happens is that exponential relationship becomes a linear one, which makes the data analysis much easier, because our third and final point for our data analysis is that if we use logarithms, we can simply calculate the gradient of this graph, and this will be the order with respect to A. So that's why we use a logarithmic graph there, because it enables us to more easily find the order with respect to A. Whereas if we simply plotted a standard graph without using logarithms for our scales, what we end up with is a curved graph, which we would then have to really study the shape of the graph in order to determine the order. Whereas this way, the order is just the gradient. So those are our 3 stages for this question. We start with the preparation, which is the quickest stage. All we need is pointing out we're measuring out known volumes of A, B, C, and X into separate containers. That covers the 3 points, A, B, C, X, and separate containers. Then procedure's longer. We need to talk about what we're actually doing in terms of mixing them together, as well as how we're getting our data and all our control variables, which must be stated, they can't be left assumed. And finally, we go on to an analysis where we need to state what we were using as a measure of initial rate, as the question asked specifically how about a measure of the initial rate of reaction, so we need to distinctly link that to it. Then talk about what we're plotting on the graph, and then how we're going to use that graph in order to get the marks. And that gives us a complete explanation of all 3 stages present in the question, which would get us the full 6 marks. The elements sodium to sulfur in period 3 all react with oxygen to form oxides. Given an equation and 2 observations made for the reaction that occurs when sodium is heated in oxygen. This question is worth 2 marks. So we're going to get 1 mark for the equation and then 1 mark for the observations. We need both of those observations to get that mark for the observations. So to begin with, we need the equation. So we're told that sodium is heated in oxygen, and that the elements in period 3 will react with oxygen to form oxide. So even without this even without prior knowledge, we could easily determine that we're going to see sodium plus oxygen produce sodium oxide. So sodium will take a ionization state of +1, whereas oxygen will be a -2. So we're going to see Na2O for our formula for sodium oxide, as that will give us a nice neutral compound. Then we need to balance this. So we have, if we begin by looking at the oxygens, we can see we have 2 on this side, but only 1 on this side. So we're going to fix that by simply having a 2 for our sodium in front of our sodium oxide. However, if we now look at our sodium, we can see we've got 1 on this side and 4 on this side. So we can fix that by putting a 4 in front of the sodium. Now that we've got our first mark for our equation, we need to get both observations right to get the second mark. So the first observation we're going to see is because the sodium is being heated in oxygen, so we're going to see a yellow-orange flame be produced. So yellow-orange flame. You could also refer to this as a yellow-orange light instead, and it would still be considered to be correct language, you can still get the mark for that. Observation 2 is about what we're going to see due to the formation of the product. So we are going to see the formation of a white powder, which is our sodium oxide. So our second observation is a formation of a white powder. And if we get both of those observations correct, that's the second mark. The first comes from the equation, and that's all we need for this question. Given the equation and one observation made for the reaction that occurs when phosphorus is heated in oxygen. This question is worth 2 marks. We're going to get one of those for the equation and one for the observation. So to begin with, the equation, what we're going to see is phosphorus being heated in oxygen means that we're going to get phosphorus plus oxygen is going to produce phosphorus oxide. So phosphorus oxide, in order to get a neutral compound, phosphorus gives as a +5 ionization state and oxygen gives us a -2. So to get a neutral compound, we need phosphorus 4 for a total of +20 and oxygen 10 for a total of -20 there to get a total of 0 overall. Then we need to balance this for the actual atoms on either side. So we've got 2 oxygens here and 10 here. So we need 5 molecules of oxygen to give us the correct number of oxygens. And then for phosphorus, we have 1 here and 4 here. So all we need is a 4 there to balance that out. So that's the balanced equation. That's the first mark. The second is for our observation. So what we'd expect to see whenever we're heating one of these elements to produce an oxide, we're going to see a flame of some kind, and part of the observation requires that we specify the color. So what we would see on heating the phosphorus, we would see a white flame. That gets us our second mark after we got the first mark from our equation, so that's both marks of the question, and that's all we need. The melting points of the highest oxides of the elements sodium to sulfur are shown in table 2. Explain the increase in melting point from sodium oxide to magnesium oxide. This question is worth 2 marks, which means there are going to be 2 key points in our answer that we need to get full marks for this question. So the reason for this increase in melting point between sodium oxide and magnesium oxide comes down to the electron configuration of these individual elements, and specifically what happens when they are ionized to produce the oxides. So sodium will produce a +1 ion and magnesium will produce a +2 ion. And this means that the magnesium ion has a greater charge, as it is +2 compared to sodium's +1. So it has a greater charge than the sodium ion. And this is due to the actual number of s sublevel electrons present in the magnesium versus the sodium. The magnesium has 2 to lose, so it becomes a 2+ ion when it ionizes. However, we now need, that's our first point as to what's going on with the within the compounds, but we need to actually now explain why that's going to affect the melting point. So the magnesium has a greater charge than sodium ion, so it has a stronger attraction to the oxygen anions than the sodium ion does. This means that because it's more strongly attracted, it's harder to actually break that attraction, and well, not fully break it, but weaken those ionic bonds in order to actually melt the sodium oxide, in order to actually melt the oxide. So it has a stronger attraction to the oxygen anions, which is this, and this attraction is the ionic bond itself, so that means it's got stronger bonding than sodium oxide. So as a result, it's got a higher melting point, and that's what causes this increase in melting point. So 2 marks for that, the first for pointing out the greater ionic charge, and the second for explaining that that means a stronger attraction to the oxygen anions. That's all we need for the question, that's both marks. Explain why the melting point of the oxide of silicon is much higher than that of the highest oxide of phosphorus. This question is worth 3 marks. So there are 3 key points we need to cover in order to gain full marks for this question. So in order to explain this difference, we're going to talk about the structures of the two oxides. So we're going to start with the structure of silicon oxide and how the actual bonds and atoms within it are laid out. So silicon oxide has what's known as a macromolecular, which is a macromolecular structure, which is also referred to as a giant covalent structure. It means that it's a giant structure with covalent bonds connecting all of it. It's quite a strong structure. However, silicon oxide has got this macromolecular. However, whereas our phosphorus oxide, it is not macromolecular. Phosphorus oxide, instead of being macromolecular, is simple molecular or simple covalent. Instead of being this one enormous structure, it is instead composed of several individual simple molecules. And this has an effect on its melting point. And the reason for this is that the bonds in silicon oxide structure, which are the covalent bonds, they extend right throughout the structure. The bonds in this structure are much stronger than the intermolecular forces that join the molecules of phosphorus oxide together. This means that it's harder to actually weaken these bonds in silicon oxide than it is to weaken the intermolecular forces between molecules of phosphorus oxide. And because it's harder to weaken them, it means that we need more energy to do so, which means that it requires more energy to melt it, so it's got a higher melting point. So that's all we need for the 3 marks. Specifically, the marks come from, the first one comes from saying about the structure of silicon oxide, the second for the structure of phosphorus oxide, and the third for a comparison showing that the silicon oxide structure is stronger because it's macromolecular, it's got these covalent bonds all throughout it, than the phosphorus oxide structure, which is weaker because it's only got these intermolecular forces there. So that's the 3 marks of the question, so that's all we need for it. A sample of the highest oxide of phosphorus was prepared in a laboratory. Describe a method for determining the melting point of the sample. State how the result obtained could be used to evaluate its purity. This question is worth 3 marks, so there are 3 points we need to make in our answer in order to gain full marks of the question. So to begin with, the first thing we need to do in order to determine the melting point is to actually place our sample. So we're going to place the sample into a suitable melting point apparatus. So depending on the nature of the sample, depends exactly which apparatus we want to use. But one example is a field tube. So a suitable melting point apparatus, such as a field tube, which is spelt THIELE tube, field tube. So the first thing to do is actually to place our sample into the melting point apparatus. We need specific apparatus for it. We can't just kind of heat it on a evaporating dish or something and then kind of keep an eye on the temperature. We want to use specific apparatus to determine it accurately. What we do then is, once it's in there, we are then going to heat the sample gradually. We need to heat it gradually rather than just very intensely and heating it to a very high temperature very quickly, because we need to be able to determine its melting point accurately. So we need to heat it up slowly so that we can see the range over which it melts. So that gives us a method to actually determine the melting point. Next thing we need to do, though, is actually explain how we could use this to evaluate how pure it is. And there's two ways we could do it. The first is the first point about the purity is that a broad melting range. So if it melts over a wide range of temperatures rather than at a very specific, precise point, indicates that this is impure. It indicates impurities. This is because we've got more than one compound present in the sample if it's impure. So these impurities in the sample, these different compounds are melting at different points, and that's what gives us this range of melting points. We could also talk about how the melting point should correspond exactly to the data book value for the melting point. So we have 3 points there. The first about using suitable apparatus, so a field tube is one example. The second is for heating it gradually, and the third is for making a comment on its purity, such as about the broad melting range or data book values. And that is the full 3 marks for the question.
Cyclohexene has a boiling point of 83 degrees Celsius, and it can be prepared by the dehydration of cyclohexanol with a boiling point of 161 degrees Celsius, using concentrated phosphoric acid. A student prepared cyclohexene by placing 10 centimeters cubed of cyclohexanol with a density of 0.96 grams per centimeter cubed into a round bottom flask. 3 centimeters cubed of concentrated phosphoric acid were then carefully added to the flask. The student added a few anti-bumping granules and set up the apparatus shown in Figure 3. The student heated the mixture and collected the liquid that distilled at temperatures below 100 degrees Celsius. The distillate was poured into a separating funnel and washed by shaking with sodium carbonate solution. Periodically, the separating funnel was inverted and the tap opened. The aqueous layer was discarded and the final organic product was dried using anhydrous calcium chloride. After the product was dried, the drying agent was removed by filtration under reduced pressure. The student collected 5.97 grams of cyclohexene in the experiment. Calculate the percentage yield of cyclohexene. The first thing we need to do with this question is highlight the key pieces of information. So that's the volume of cyclohexanol and its density, and that we've got the structures of cyclohexanol and cyclohexene, also the mass of cyclohexene that we collect. So this is all the important information that we're going to use to help work out the percentage yield of cyclohexene. The equation triangle we're going to use in this question is where we have mass is equal to moles times the relative formula mass. So the first thing we need to do is work out the relative formula mass of cyclohexanol and cyclohexene. So if we start with cyclohexanol, that's going to be 6 times 12 plus 12 plus 16, which equals 100 grams per mole. Then if we do cyclohexene, that's going to be 6 times 12 plus 10, which equals 82 grams per mole. Next, we need to work out the mass of cyclohexanol. We've already got the mass of cyclohexene from the question here, which is 5.97 grams. But we don't have the mass of cyclohexanol. However, we can work it out using its density and volume. And it's going to be 10 multiplied by 0.96, which is equal to 9.6 grams. Next, we're going to work out the moles of cyclohexanol, and that's because we've got a 1-to-1 molar ratio, so the moles of cyclohexanol will also be the maximum moles of cyclohexene, so we can use these moles to work out the maximum mass of cyclohexene. So, working out the moles, that's going to be 9.6 divided by 100, which is the relative formula mass of cyclohexanol. And that is going to equal 0.096 moles. Then we're going to do 0.096 times 82, and that equals 7.87 grams, which is the maximum mass of cyclohexene that we could produce in this question. And because we know what we actually produce, we can use these two masses to work out percentage yield. We can do 5.97 divided by 7.87 multiplied by 100 to convert it into a percentage, and you get 76%. But there is an alternative method to this question. So this alternative method, instead of using mass, you use moles. So we already know the maximum theoretical moles of cyclohexene that we can produce, and that's the same as the moles of cyclohexanol because it's a 1-to-1 ratio. But then we need to work out the moles of cyclohexene. So that's going to be 5.97 divided by 82, which equals 0.0728 moles. So that's again using the equation triangle that we have on the previous slide, which is mass is equal to moles times relative formula mass. So if we then put this as the numerator, 0.0728 and multiply by 100, that's also going to equal 76%, which is our percentage yield for this question. So to get the 3 marks for this question using our first method, you get a mark for working out the moles of cyclohexanol, so 0.096. You get a mark for working out the mass or the maximum mass of cyclohexene, and then you get your final mark for dividing the two masses and calculating your percentage yield. If you use the alternative method where you use moles, you again get a mark for working out the moles of cyclohexanol. You then get a mark for working out the moles of cyclohexene, which is 0.0728, and then you get your final mark for dividing these two moles, multiplying by 100 and getting 76 as your percentage yield. Describe a test tube reaction on the product to show that the cyclohexanol had been dehydrated. State what you would observe. So what this question is actually asking you for is the test for an alkene, because when this reaction happens, you're going from an alcohol to an alkene. And the test for an alkene is that if you add bromine water, there's going to be a colour change, which will go from orange to colourless. Or you can say that if you add bromine water, it will decolorise if you've got an alkene present. To get the 2 marks for this question, you get a mark for saying that you're going to add bromine water, so the test for an alkene. And then you get your second mark for the positive result, which is that it will decolorise or turn from orange to colourless. Suggest why sodium carbonate solution was used to warm the distillate. So a really common use of a carbonate is to test for acid. And what happens is sodium carbonate will neutralise the distillate because it's going to react with or remove the phosphoric acid. You could also write this as H+. To get the mark for this question, you need to write this statement. Explain why it is important to open the tap of the separating funnel periodically. So this is a really good practical question. So when you shake a separating funnel, you need to open the tap, and that is to avoid pressure buildup. When you first open the tap, you'll hear a kind of whooshing noise, and that is the initial pressure being released. So you can also say release pressure or release carbon dioxide because that's the gas that's building up in the separating funnel, or to prevent the stopper blowing out. To get the mark for this question, you need to write this statement on the answer lines provided. Give a property of anhydrous calcium chloride other than its ability to absorb water that makes it suitable as a drying agent in this preparation. So another characteristic of anhydrous calcium chloride, other than its ability to absorb water that's relevant in this question, is that it won't dissolve in or react with cyclohexene, which is our product in this question. To get the mark for this question, you need to write this statement on the answer lines provided. Describe the apparatus used to remove the drying agent by filtration under reduced pressure. Your description of the apparatus can be either a labelled diagram or a description in words. So for this question, I'm going to draw the diagram or the labelled diagram and then talk through how you would write the description if you didn't want to draw a labelled diagram. So we need to start with what's called a Buckner funnel, and the key characteristic of a Buckner funnel is that it's got a side arm, and this side arm is connected to a vacuum pump. So this is our first label, and then we're going to also label that it's a Buckner flask. Then we need to draw on a Buckner funnel. So that has a airtight seal, and it kind of looks like this, where it's not a classic funnel shape, it's a bit more angular, and it will have filter paper inside. So it's a Buckner funnel with filter paper. So this is going to be our third label. Then if you wanted to talk through the apparatus rather than drawing it, you would need to talk about having a Buckner flask that is connected to a vacuum pump via its side arm, and that you have a Buckner funnel and a filter paper in your Buckner funnel, and it's an airtight seal. So you can tell here on the diagram that it's airtight because there's no spaces in the funnel and the flask. So that's how you get the 2 marks for this question. So 1 mark for your basic diagram, 1 mark for the labels, or 1 mark for Buckner flask connected to vacuum pump, and your other mark for Buckner funnel with filter paper. A sample of cyclohexene has been contaminated with cyclohexanol. The cyclohexene can be separated from the cyclohexanol by column chromatography. Silica gel is used as the stationary phase and hexene as the mobile phase. Explain why cyclohexene has a shorter retention time than cyclohexanol. The first thing to do with this question is to talk about the polarity of our 2 compounds. So cyclohexene is much less polar than cyclohexanol. Cyclohexanol has an OH functional group, which means it can form hydrogen bonds very easily, and so it's a lot more polar. Then we need to talk and address the question. So why does cyclohexene have a shorter retention time than cyclohexanol? And that's because cyclohexene has a greater affinity for the mobile phase, which is hexane. So if it's got a greater affinity for the mobile phase, it's going to move very quickly through the column chromatography. To get the 2 marks for this question, you get 1 mark for talking about the polarity and saying that cyclohexene is less polar than cyclohexanol. Alternatively, you could have said that cyclohexanol is more polar than cyclohexene. Either would get you the 1st mark for this question. And then you get your 2nd mark from saying that cyclohexene has a greater affinity for the mobile phase, or for hexane. Or you could have said that cyclohexanol has a greater affinity for the stationary phase, or silica. Explain how an infrared spectrum would confirm that the cyclohexene obtained from the chromatography column did not contain any cyclohexanol. So to confirm that there's not any cyclohexanol in an infrared spectrum, there won't be a peak at between 3,230 to 3,500 centimeters to the -1 because you're losing the OH peak in the IR spectrum. So this statement will get you the mark for the question. Alternatively, you could have said that there's going to be no additional peaks in the fingerprint region compared to a pure sample, or that the fingerprint region exactly matches cyclohexene. A student carried out an experiment to find the temperature rise for a reaction between hydrochloric acid and sodium hydroxide solution. The student used a measuring cylinder to place 50 centimeters cubed of 0.4 moles per decimeter cubed hydrochloric acid into a glass beaker. The student recorded the temperature at 1-minute intervals for 3 minutes. At the 4th minute, the student added 50 centimeters cubed of 0.4 moles per decimeter cubed sodium hydroxide solution and stirred to mix the solutions, but did not record the temperature. The student recorded the temperature at 1 minute intervals for a further 8 minutes. The results are shown in Table 3. Plot a graph of temperature against time on the grid opposite. Use your graph to find the temperature rise delta T at the 4th minute. Show your working on the graph by drawing suitable lines of best fit. So here I've plotted all the data from Table 3. The key things to notice is that the y-axis doesn't start at 0, it starts at 18, and that each small square is 0.05 of a degree. So this is meaning that the y-axis can be really accurate, and they are looking that you don't start it at 0 on the y-axis. If you do, but you can fit all the numbers in your graph, then they will allow it, but they prefer you to start at 18 or 19 degrees. But time can start at 0 because it has to. You do have a measurement at time 0, so that's also very important. So now we need to tackle the question. So we've already plotted a graph of temperature against time, and now we need to find the temperature rise at the 4th minute by drawing suitable lines of best fit. So we have to draw 2 lines of best fit in this question. So our first line of best fit is going to be here, and then our second line of best fit will just be a straight line through 19.8 degrees Celsius. So now we can work on our temperature rise. So if we look and find where on this first line of best fit we cross 4 minutes, that's going to be here at 21.9 degrees Celsius. And we already know that at the 4th minute here, we're going to be at 19.8. So our temperature rise is going to be 21.9 minus 19.8, which equals 2.1 degrees Celsius, which we can write on the answer line provided. To get the 5 marks for this question, you get your first mark for plotting temperature on the y-axis and using sensible scales, such as a minimum of 20 little squares for each degree Celsius on the y-axis, which we've used here. You get your second mark for plotting all of the points correctly, plus or minus half a small square. You get your third mark for drawing 2 lines of best fit, one from 0 to 3 minutes and one from 6 to 12 minutes. So not using the 5-minute point, that's the key here. Then you get your 4th mark for extrapolating both lines to at least the 4th minute. So that's where this green point comes in on both lines of best fit. And then you get your 5th mark for working out the temperature rise of 21.9 minus 19.8, which is going to equal 2.1 degrees Celsius. The uncertainty in each of the temperature readings from the thermometer used in this experiment was plus minus 0.1 degrees Celsius. Calculate the percentage uncertainty in the value for the temperature rise. So the key parts of this question is the uncertainty for temperature readings and that we want the percentage uncertainty for temperature rise. So the equation that we're going to use is our uncertainty, which is 0.1, multiplied by how many times we've used it to calculate temperature rise. So we use 2 temperature readings and we subtract them to work out temperature rise. So we need to multiply by 2. And then you divide by the value that you find, which is 2.1 degrees Celsius. And then we multiply by 100 to calculate a percentage. And this equals 9.5%, which we can write on the answer line as the percentage uncertainty. To get the mark for this question, you need to write 9.5%. Suggest a change to the experiment that would minimise heat loss. So minimising heat loss is a really common issue, and in homes we use insulation. So we're going to apply the same principle. A polystyrene cup will insulate a lot better than a glass beaker. So one way we can minimise heat loss is by replacing the glass beaker with a polystyrene cup. Or we could just insulate the glass beaker and we could use a lid, so this would prevent evaporation and keep the heat inside the glass beaker as much as possible. To get the mark for this question, you get a mark for the statement of replace the glass beaker with a polystyrene cup or insulate the glass beaker, or use a lid. Suggest and explain another change to the experiment that would decrease the percentage uncertainty in the use of the same thermometer. When you calculate percentage uncertainty, you take the uncertainty of your instrument and divide it by your temperature rise. Now, we can't do anything about the uncertainty of the instrument, but we can change the temperature rise. And if we want to decrease percentage uncertainty, we want the denominator of this fraction to be bigger, so that means we need a bigger temperature change or temperature rise. And we do this by increasing the concentration of our acid or alkali, so when you add it at 4 minutes, you're going to get a steeper line of best fit on your graph and therefore a bigger temperature rise. To get the 2 marks for this question, you get a mark for increased magnitude of temperature change, and then a mark for by increasing the concentration being the key word here, of the acid or alkali. A second student completed an experiment to determine the enthalpy of neutralization for the reaction between ethane dioic acid solution, HOOCCOOH, and potassium hydroxide solution. The student added 25 centimeters cubed of 0.8 moles per decimeter cubed ethane dioic acid solution to 75 centimeters cubed of 0.60 moles per decimeter cubed potassium hydroxide solution. The temperature increased by 3.2 degrees Celsius. Give an equation for the reaction between ethane dioic acid solution and potassium hydroxide solution. Calculate the enthalpy change per mole of water formed in this reaction. Assume that the specific heat capacity of the reaction mixture is 4.2 joules per Kelvin per gram, and assume that the density of the reaction mixture is 1 gram per centimeter cubed. Let's start by highlighting the key pieces of information in this question. So that's the volume and concentration of ethane dioic acid solution, the volume and concentration of potassium hydroxide solution, the temperature increase, also that we want to calculate the enthalpy change per mole of water formed in the reaction, the specific heat capacity and the density of our reaction mixture. The first thing we're going to do is write an equation for the reaction between ethane dioic acid solution and potassium hydroxide solution. So ethane dioic acid is 2 carboxylic acids joined together with a carbon-carbon bond. And when you react with a base or an alkali, such as potassium hydroxide, you're going to produce carboxylate ions. An example of a carboxylate ion is here, where in the carboxylic acid you'd normally have your OH. In a carboxylate ion, this OH becomes an O-. So that's going to be what we produce, and it's going to bond with the positive potassium. So writing our equation, we've got HOOCCOOH, which is our ethane dioic acid solution, plus potassium hydroxide, and then we're going to produce 2 carboxylate ions, either end of our ethane dioic acid. So that's OOCCOO, and that's going to be ionically bonded to potassium, but we need 2 potassiums because we need 1 for each end. And then we're also going to produce water, but we need to balance this equation. We need 2 potassium hydroxides and we need 2 waters. So this is the first bit of the question done. Now we're going to use our first equation of the question, and that is that Q is equal to mc delta T. So M is going to be the total volume or the total mass of our solution, which is 25 centimeters cubed plus 75 centimeters cubed, which is 100 centimeters cubed. But because we have a density of 1 gram per centimeter cubed, that's also going to be our mass of 100 grams. C is specific heat capacity and delta T is the temperature change. So we have all this information. We can work out Q, which is going to be the energy in joules, and it's going to be 100 multiplied by 4.2 multiplied by 3.2. And that's going to equal 1,344 joules, or 1.344 kilojoules. So here we've got the kilojoules, and now we need to work out the per mole part of the kilojoules per mole units. To do this, we're going to need another equation, and it's going to be an equation triangle of moles is equal to volume times concentration. So we have the volume and concentration of ethane dioic acid and potassium hydroxide, so we're going to work out the moles of both. If we start with ethane dioic acid, that's 25 times 10 to the negative 3, because we convert centimetres cubed into decimeters cubed, and then we multiply by 0.8, and that's equal to 0.02 moles. Then we do the same for potassium hydroxide, so that's 75 times 10 to the negative 3 multiplied by 0.6, which equals 0.045 moles. So we would expect the moles of potassium hydroxide to be about double, because we have a 1:2 ratio of potassium hydroxide, but they're over double, so we can't use them to work out the moles of water. Instead, we take the lower moles, which is 0.02, and that's the moles of ethane dioic acid, and then we multiply this by 2. So 0.02 multiplied by 2 is equal to 0.04 moles of water. And we multiply it by 2 because we have a 1:2 molar ratio of ethane dioic acid to water. And now we have the moles of water, we can work out kilojoules per mole. So that's going to be 1.344 kilojoules divided by 0.04, which is equal to 33.6 kilojoules per mole. The final part of the question is that we need to work out if this is exothermic or endothermic. So an exothermic reaction will release heat into its surroundings. And that's exactly what's happening in this question. We know because we've got heat loss to the surroundings, which we mentioned in the last question. And this is a very similar reaction to the last question, where you have an acid and a base and you react them in a neutralization reaction, and you're going to produce some heat. So it's going to be an exothermic reaction due to this heat production and heat loss to the surroundings. So that means that our enthalpy change will be negative. If it's endothermic, it's positive. If it's exothermic, it's negative. To get the 5 marks for this question, you get a mark for your equation being correct and balanced. You get a mark for working out the energy in joules or kilojoules, but either gets you the second mark. Then you get a mark for the moles of ethane dioic acid that you worked out, and a mark for the moles of potassium hydroxide that you worked out. You get a mark for the moles of water, and then you get your final mark for the enthalpy change of neutralization. In a similar experiment to that in question 4.5, the enthalpy of neutralization for the reaction between sulfuric acid and potassium hydroxide solution was found to be minus 57.0 kilojoules per mole of water formed. Suggest an explanation for the difference between this value and your answer to question 4.5. If you were unable to obtain an answer to question 4.5, you should assume a value of minus 28.5 kilojoules per mole. This is not the correct answer. The differences between this experiment and the previous questions experiment is the acid that you're using, so you've got sulfuric acid versus ethane dioic acid, and that the enthalpy change of neutralization is a lot more exothermic for this experiment, whereas the one in the previous question is more endothermic, it's more positive. So ethane dioic acid is a weak acid, and that means it doesn't fully dissociate. If it doesn't fully dissociate, that means that more energy is needed to break the bonds and to have complete dissociation. Dissociation is endothermic, which we can see from the 2 values. Ours is a lot more positive, whereas when you use a stronger acid, it's a lot more negative. It's a lot more exothermic because Strong acids fully dissociate and don't need this extra energy to dissociate. To get the 2 marks for this question, you get a mark for saying that ethane dioic acid is a weak acid, so it doesn't fully dissociate. That's your first mark. And then your second mark comes from saying that more energy is needed to break bonds, or complete dissociation, or that dissociation is endothermic. All of those can get you your second mark for this question. Which can be both an empirical and molecular formula of a stable compound? A. CH2O, B. P4O10, C. NH2, or D. CH3. The key in this question is that we're looking for an empirical and molecular formula of a stable compound. So empirical formula is the simplest way you can write a molecular formula. So if it can be divided by 2, that would be the empirical formula. And that brings us to B. Well, both of these can be divided by 2 and you get P2O5 as your empirical formula and P4O10 as your molecular formula. So our answer can't be B. Then we look at C and D. So this is focusing on the stable compound. Nitrogen prefers to have 3 bonds. So for example, ammonia is NH3 and it will have its lone pair and produce a stable compound of ammonia. Carbon prefers to have 4 bonds, like methane, where we have carbon and then 4 hydrogens. So the bond shapes for these 2 stable compounds are tetrahedral with a bond angle of 109.5 degrees, and then trigonal pyramidal with a bond angle of 107 degrees. So these are both stable compounds, but NH2 and NH3 aren't because they don't have the right number of bonds to make the central element stable, so nitrogen or carbon. And then we come to look at A. Well, carbon wants 4 bonds, but oxygen wants 2. So we have a carbon-oxygen double bond and then 2 hydrogens. So this is going to be an aldehyde and it's going to be methanol. And so our answer for this question is A, because A also can't be divided by anything to get a simpler version of this molecular formula. So it's also the empirical formula. And to get the mark for this question, you need to circle the box that says A. Which diagram shows the correct bonding and correct bond polarity in a molecule of oxygen difluoride? And we're given 4 different possibilities. Let's start by looking at the correct bonding. So oxygen wants to form 2 bonds, like we looked at in the last question. And it can very comfortably form 2 covalent bonds with fluorine. The arrows in B and C show dative covalent bonding, but oxygen doesn't need dative covalent bonding. It can very easily form a normal covalent bond with fluorine, where 1 electron is put into the bond from fluorine and 1 from oxygen. So we can eliminate B and C. Now we need to look at the bond polarity. So fluorine is a lot more electronegative than oxygen, which means it's going to have a delta negative charge, and oxygen is going to have a delta positive charge because it's more electropositive. And so we can eliminate D. So to get the mark for the question, you need to circle the box with A. In the early 20th century, the apparatus shown in the diagram was used to investigate atomic structure. When helium-2+ particles were fired at a thin sheet of gold, most of the particles were detected at point P. What conclusion can be drawn from the detection of helium-2+ particles at point P? A. Gold atoms contain electrons. B. Gold atoms contain protons. C. Gold atoms contain neutrons. Or D. Gold atoms are mainly empty space. The key in this question is that you can detect the helium particles at point P, which is here on the diagram. So this is a sign that the gold atoms are mostly empty space. And that's because if it came into contact with a nucleus, a positive nucleus of the gold, then the helium-2 plus particles would be deflected, because a positive and a positive charge will repel each other, and so it wouldn't be able to pass straight through to point P. But the fact that it can means that these gold atoms are mostly empty space. And therefore, to get the mark for this question, you need to circle the box that corresponds to D. Helium-2 plus particles were fired at a thin sheet of gold. About 1 in 8,000 of the particles were detected at point Q. What conclusion can be drawn from the detection of helium-2 plus particles at point Q? A. Gold atoms have a small positive nucleus. B. Gold atoms have electrons in orbitals. C. Gold consists of ions in a sea of delocalized electrons. Or D. Gold atoms have more protons than helium-2 plus particles. The key in this question is that we're detecting our helium-2 plus particles at point Q, which is here on the diagram. And what's happening is the helium-2 plus particles are coming into contact with gold's positive nucleus, and they're being deflected by the gold sheet. Atoms are mostly empty space, and that's why 1 in 8,000 of the particles are detected at point Q, because the majority aren't going to come into contact with gold's positive nucleus, and they're going to pass straight through the gold sheet. But 1 in 8,000 will come into contact with its nucleus and will be deflected to point Q. And so what this is a sign of is that gold atoms have a small positive nucleus. It needs to be small because it's only 1 in 8,000, and it needs to be positive so that when the helium-2 plus, so positive particles, come into contact with it, they will be deflected. So to get the mark for this question, you need to circle the box corresponding to A. Which equation represents a termination step? We're given 4 different possibilities for this question. A termination step is the final stage in a free radical substitution reaction, and it's where you take 2 radicals and you react them together to form something that's not a radical. And the only one of these possible equations that does that is D, because the other 3 only have 1 radical reacting with something that's not a radical and producing a radical and something else, or just a radical. So our answer has to be D, because this is the only one where you react 2 radicals together and form a compound that's not a radical. So to get the mark for this question, you need to circle the box corresponding to D. Which statement is correct about the molecule shown? A. It reacts with HBr in an electrophilic substitution reaction. B. It reacts with NaBH4 in a nucleophilic addition-elimination reaction. C. It reacts with ethanolic potassium hydroxide in an elimination reaction. Or D. It reacts with KCN in a nucleophilic substitution reaction. So let's talk through each statement. A. We have hydrogen bromide and electrophilic substitution. Well, hydrogen bromide is the reagent for electrophilic addition. But if we had electrophilic addition written, what would happen is the double bonds would become single bonds, so that's where the hydrogen comes in. It gets added to this double bond and makes it a single bond. And then you can get bromine added here or here, depending on if you want the major or the minor product. So this would be the major product and this would be the minor product, because the major product has a more stable carbocation intermediate. So it would have the positive charge here, where you've already got a CH3R group added, whereas if you had your positive charge here, you have a hydrogen, so it's a lot lower as a carbocation intermediate. So the left-hand carbocation intermediate would be tertiary, and the right-hand carbocation intermediate would be secondary. And therefore you can see how the left hand will be a lot more stable, and this is going to be the major product. But this is for an electrophilic addition reaction, and the question does say electrophilic substitution, which is incorrect. So our answer can't be A. Now let's look at B. NaBH4 is the reagent used in nucleophilic addition reactions, but not a nucleophilic addition-elimination reaction. If we had a nucleophilic addition reaction, what would happen is this aldehyde would turn into an alcohol, and you would get an additional hydrogen because you want carbon to have 4 bonds, and the carbon-oxygen double bond will turn into a carbon-oxygen single bond. But again, we're not asked for nucleophilic addition, we're asked for nucleophilic addition elimination, which NaBH4 is not the reagent for. So our answer can't be B. Then if we look at ethanolic potassium hydroxide and its elimination reaction, what would happen here is the bromine, or the haloalkane, will get lost, that's going to be eliminated, and in its place you're going to get either a double bond here or a double bond here. But because we have these two double bonds, we can't physically add another double bond due to our methyl groups, because that would mean that carbon has 5 bonds, and carbon can't have 5 bonds, it has to have 4. So therefore, there aren't stable products if we used ethanolic potassium hydroxide in an elimination reaction for this molecule. So our answer can't be C, which just leaves us with D. So let's take a closer look. So what's going to happen is the CN will become CN-. It's going to become the nucleophile. There's going to be a delta positive carbon and a delta negative bromine. The nucleophile will be attracted to the delta positive carbon, and the delta negative bromine will be kicked off. So the nucleophile, the CN- nucleophile, will replace the bromine, and it will get kicked off as Br-. So looking at the details, KCN is the correct reagent for nucleophilic substitution. And that's the key in this question. It's looking at the reagents and looking at the reaction that they propose and seeing if they match up. So to get the mark for this question, you need to circle the box that corresponds to D. Which statement is correct about both 2-methylbutan-1-ol and 2-methylbutan-2-ol? A. They can be formed by alkaline hydrolysis of esters. B. They can be oxidized by reaction with acidified potassium dichromate. C. They can be formed by hydration of 2-methylbutyrene. Or D. They have 4 peaks in their carbon-13 NMR spectra. The key in this question is that the statement has to be correct for both 2-methylbutan-1-ol and 2-methylbutan-2-ol. So let's start by drawing these structures. We need a 4-carbon chain for both because of butanol. Then we need a methyl group on carbon number 2 for both of them. And we need an OH group on carbon number 1 and then carbon number 2. So here we have our 2 structures. And now let's work through each statement. So can be formed by the alkaline hydrolysis of esters. So the key here is that it's alkaline hydrolysis. So acid hydrolysis, you will form the carboxylic acid and alcohol used to make the ester. But with alkaline, what you form is the salt of the acid and then the alcohol. And because they don't specify the ester that you're hydrolyzing, this is actually correct because both have the alcohol group and both can form esters with a carboxylic acid from this alcohol group and can be hydrolyzed using a base, using an alkali. So A is the answer for this question, but we need to check the other statements first. So they can be oxidized by the reaction of acidified potassium dichromate. So we need to look at if they're primary, secondary or tertiary alcohols. So 2-methylbutan-1-ol, that is a primary alcohol. And then 2-methylbutan-2-ol is a tertiary alcohol. Tertiary alcohols can't be oxidized, so our answer can't be B. Then if we look at C, they can be formed by the hydration of 2-methyl-butene. So let's draw this out. We need a 4-carbon chain, and then we have a double bond on carbon number 2 and a methyl group on carbon number 2. So what would happen with the hydration of 2-methyl-butene is you would either get an OH group here or an OH group here. So this second OH group is correct for 2-methyl-butanol. But the first one, where we have it on carbon number 3, this isn't 2-methyl-butanol. So this can't be correct. You'll only form 2-methyl-butanol from this method. So our answer can't be C. And then we need to look at how many peaks each of them have in a carbon-13 NMR spectra. So let's start with 2-methyl-butanol. We have 1, 2, 3, 4, 5 peaks in our carbon-13 NMR spectra. So that's not 4, so our answer can't be D. But if we just check and look at 2-methyl-butanol, just to double check that this is definitely incorrect, I mean it can't be correct because 2-methyl-butanol has 5, but just for clarity, 2-methyl-butanol has 1, 2, 3, 4 peaks in the carbon NMR spectra. So if you didn't check both and you started with 2-methyl-butanol, you might assume that it can have 4 peaks in the carbon-13 NMR spectra. But this is incorrect because not both of them have this. So the answer for this question is A, and to get the mark for the question, you need to circle the box that corresponds with A. Solutions of two compounds W and X react together in the presence of a soluble catalyst Y, as shown in the equation. When the concentrations of W, X and Y are all doubled, the rate of the reaction increases by a factor of 4. Which is a possible rate equation for this reaction? A. Rate is equal to K times the concentration of W squared times the concentration of X. B. Rate is equal to K times the concentration of W squared times the concentration of Y. C. Rate is equal to K times the concentration of X times the concentration of Y. Or D. Rate is equal to K times the concentration of X times the concentration of Z. The key in this question is that we have the concentrations of W, X and Y. We are doubling their concentration, and the rate of the reaction increases by a factor of 4. So what this means is we want an overall rate equation which is second order. So that means that we have 2 rates that add up to 2. And so when we double them, they'll be first order each, or one will be second order and the other one will be 0th order. And when we double this concentration, the rate will increase by a factor of 4. So if we look at our 4 different possibilities and we identify if they have an overall rate order of second order. So looking at A, we have an overall third order reaction because we have 2 plus a 1, so that's 3, so it can't be A. Then if we look at B, again, this is a third order overall rate equation, so it can't be B. Then looking at C, well, we have a second order rate equation, so this can be a possibility, and then so does D. But then we need to look back on the question, and we have an X and a Z, or an X and a Y. So we're asked when the concentrations of X, Y and W are doubled, not Z. So it can't be D because they aren't doing anything to the concentration of Z. And so our answer is C. And to get the mark for this question, you need to circle the box that corresponds to C. A series of experiments was carried out to find the order of reaction with respect to reactant X. In these experiments, only the concentration of X was changed. Which graph would show that the reaction is second order with respect to X? A, B, C or D? So the key thing to notice about this question is the units of the Y and the x-axis. So using these two units, we have C being first order and D being second order. But a lot of people would maybe not get this right, because if we had the y-axis being the concentration of X and the x-axis as time, that would mean that B is 0th order and A would be first order, and if it was slightly steeper, second order. So this is a common thing with rate questions where there are two different graphs, and depending on the units of the axes, you can get the graphs muddled up. But this question is asking us for the reaction being second order with respect to X, and the only one here that's second order is D. So to get the mark for this question, you need to circle the box that corresponds to D. Which equation represents the process that occurs when the standard enthalpy of atomization of iodine is measured? A. Half I2 solid goes to I gas. B. I2 solid goes to 2I gas. C. Half I2 gas goes to 1I gas. Or D. I2 gas goes to 2I gas. So firstly, let's define standard enthalpy of atomization. So this occurs when 1 mole of a sample is dissociated into its atoms under standard conditions. So what this means is we're going from a solid to a gas, so that eliminates C and D, and we want 1 mole, so that can't be B because we have 2 moles here. It's going to be the enthalpy of atomization multiplied by 2. Instead, our answer is going to be A, because they've made sure that we're using 1 mole by putting half I2 and we make 1 iodine gaseous atom. To get the mark for this question, you need to circle the box corresponding to A. Which structure is formed by aspartic acid in solution at pH 12? And we're given 4 different structures. Let's start by drawing the structure of aspartic acid in a neutral solution. So that's going to be H2N connected to CH, COOH, and then C2H and another carboxylic acid group of COOH. Then we need to look at the next bit of the question. We've got a pH of 12, which is alkaline. So that means it's going to react with the acidic parts of our aspartic acid, which is both carboxylic acid groups. So that means our answer is going to be D. And that's because it can't be A, because it's only reacting with one acidic group in A, and both B and C have it reacting with the amine group, which it can't if it wants to react with the acidic parts, because the amine part is also alkaline, it's also basic. And to get the mark for this question, you need to circle the box corresponding to D. How many peaks are there in the carbon-13 NMR spectrum of 1,4-dimethylbenzene? A, 8, B, 4, C, 3, or D, 2? Let's start by drawing 1,4-dimethylbenzene. So that's going to be a benzene ring, which is a 6-carbon ring with a circle in the middle to signify that it's got alternating carbon-carbon double and single bonds. And then we have a methyl group at carbon number 1 and carbon number 4. So whenever we're looking at an NMR spectrum, we need to look for lines of symmetry. So in 1,4-dimethylbenzene, we have a line of symmetry across the middle and down the top. So that means when we look for the peaks, we have 1, 2, 3, and then another 3 here, following the lines of symmetry. And if we have 3, that means our answer is going to be C. So to get the mark for this question, you need to circle the box corresponding to C. Which of these period 3 elements has the highest melting point? A, aluminium, B, phosphorus, C, sodium, or D, sulfur? So let's start by drawing all the period 3 elements and then talk about the general trend in melting point. So our period 3 elements are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. So we don't need to worry about magnesium, silicon, chlorine or argon in this question. But the general melting point trend is that up till silicon, you've got quite a steady upwards trend in melting point, and then it will slightly decrease, but then as you get to phosphorus, you have a huge decrease for the rest of period 3. So this is a very rough general trend of melting point. But silicon and aluminium have the two highest in period 3. So that means the answer for this question is going to be aluminium because we don't have silicon as one of our options. To get the mark for this question, you need to circle the box correlating to A. Chlorine reacts with cold dilute aqueous sodium hydroxide. Which is a complete list of the products? A. Sodium chloride, sodium chlorate 1 and water. B. Sodium chlorate 1 and water. C. Sodium chloride, sodium chlorate 5 and water. Or D. Sodium chloride and sodium chlorate 1. Let's write the equation for this reaction. So we have chlorine, so Cl2, and sodium hydroxide, NaOH. And we are going to produce sodium chloride, which is NaCl. And that's because it's a really strong ionic compound and very stable. So we will be producing this. We're also going to produce water, so H2O. And then we need to work out what we're left with. So before we do this, we need to slightly balance the equation. And we need 2 sodium hydroxides in order to make water. So that means we're left with a sodium, a chlorine, and an oxygen. So this is sodium chlorate, but we need to work out if it's sodium chlorate 1 or sodium chlorate 5. So we can already eliminate B and D as possible answers, but we need to work out the oxidation state of chlorine in order to work out if it's sodium chlorate 1 or 5. So Na has an oxidation state of +1 and oxygen has an oxidation state of -2. And we want an overall oxidation state of 0 for this compound. So that means chlorine is going to have a +1 oxidation state as well. So that means our answer is A because it's sodium chlorate 1. And so to get the mark for this question, you need to circle the box that corresponds to A. Which products are formed when magnesium reacts with steam? A. Magnesium hydroxide and hydrogen. B. Magnesium hydroxide and oxygen. C. Magnesium oxide and hydrogen. Or D. Magnesium oxide and oxygen. The key word in this question is steam. So if it said water, so H2O liquid, rather than H2O gas, if it was water, we would produce a hydroxide, a metal hydroxide. And so that would be A or B. But because it's steam, we're going to produce a metal oxide. And that's going to be C or D. So between here, we've got the difference of hydrogen or oxygen gas. And in both cases, whether it's water or steam, we produce hydrogen gas. So that means we can eliminate D and B before we even consider if it's water or steam. But because it is steam, we're going to produce the metal oxide and hydrogen. So our answer is C. And to get the mark for this question, you need to circle the box that relates to C. Which observation would confirm that ammonia gas is released when solid ammonium chloride is warmed with solid calcium hydroxide? A. Damp blue litmus paper turns red when touched into the solid mixture. B. Damp red litmus paper turns blue when touched into the solid mixture. C. Damp blue litmus paper turns red when held just above the solid mixture. Or D. Damp red litmus paper turns blue when held just above the solid mixture. The key in this question is that we're testing for ammonia gas. And it's a gas, so that means the two options where it says that it's touched into the solid mixture, well, that's not going to be able to identify a gas. So we can eliminate A and B. So we're left with C and D now. So it's the difference between if you use blue or red litmus paper. So the test where you use blue litmus paper is actually for chlorine gas, and what will happen is it turns red and then it will start to turn white. So chlorine is not ammonia, and that means the test for ammonia is where you use red litmus paper and it will turn blue. So that's D. And to get the mark for this question, you need to circle the box that relates to D. The repeating unit of a polymer is shown. Which monomer or pair of monomers could be used to make this polymer? And we're given 4 different possibilities. So the key feature in this question is the functional group of the polymer. So that's here in the middle, and it's an amide functional group. To make an amide, you need an acyl chloride and an amine. The other key feature of this polymer is that we have alternating alkyl chains. We have one where it's CH2,4 and one where we have CH2,6. But going back to the amide for now, so we need an acyl chloride and an amine, so that already will eliminate B because that only has 2 acyl chlorides, or a diacyl dichloride. Now we need to look at the alternating alkyl chains. So that eliminates A because it will only have a CH2,4 chain at both sides, and the polymer that we've been given doesn't. It has a CH2,4 and a CH2,6. So it can't be A, so we're left with C and D. So the difference between C and D is that one starts with the CH2,4, so the diacyl dichloride has a CH2,4, and the amine has CH2,6, whereas in D this is the other way round. We have the diacyl dichloride with the CH2,6 and the amine with the CH2,4. But if we look at the polymer, the diacyl dichloride has the CH2,4. It starts with this CH2,4 around it, and the amine has the CH2,6, and that's the amine part that makes up the amide functional group. So that means we eliminate D, and our answer for this question is C. So to get the mark, you need to circle the box that corresponds to C. The structure of part of a polyester chain is shown. Which statement correctly explains why plastics made from this polyester only soften at high temperatures? A. Hydrogen bonds and van der Waals forces exist between polyester chains. B. Permanent dipole-dipole forces and van der Waals forces exist between polyester chains. C. The carbon-carbon bonds in the chain are strong. Or D. The carbon-oxygen bonds in the chain are strong. Let's look at each of these statements individually. So the difference between A and B is that one says that the chain can hydrogen bond and the other says that the chain can have permanent dipole-dipole forces. So let's look at hydrogen bonds, and that's going to be between the polymer chains. So an ester will hydrogen bond with water, but if we had 2 chains side by side, they won't hydrogen bond. And that's because to hydrogen bond, you would hydrogen bond from this carbonyl group to a hydrogen. And that would mean that this oxygen would have to have a hydrogen attached to it, which it doesn't, and therefore it can't hydrogen bond. So A is incorrect. Then if we look at B, well, that's saying does it have permanent dipole-dipole forces? And the answer to this is yes. We have a permanent positive dipole on the carbon of the carbonyl group and a negative dipole on the oxygen. And this is why you would hydrogen bond with water, because then the hydrogen from water would have a positive dipole, and then the oxygen would have a negative with another hydrogen attached. So this is an example of how you would draw hydrogen bonding with water, but because there's no hydrogen in the chains, this isn't really relevant, part A. But B is correct. We do have permanent dipoles in this polyester chain. Then if we move on to look at C and D, so they're talking about the types of bonds. So the carbon-carbon bond, which is here, and then the carbon-oxygen bond, which is here. So the carbon-oxygen bond can be very easily broken through hydrolysis. If you hydrolyze an ester or a polyester, it will break down into a carboxylic acid and an alcohol if you use acid hydrolysis. If you use base hydrolysis, you'll get the salt of the carboxylic acid and the alcohol produced. But this carbon-oxygen bond is very easy to break, so it's not strong, and therefore D is incorrect. Then if we look at the carbon-carbon bond, well, these alkyl chains, as the chain gets longer, will start to get in the way, and therefore will interrupt the temperature needed to melt or boil this polyester, and so these chains aren't strong. They will actually lower the temperature needed to soften the polyester. So C is incorrect. Therefore, that makes our answer B, and to get the mark for this question, you need to circle the box that relates to B. The nitration of benzene uses a nitrating mixture of concentrated nitric acid and concentrated sulfuric acid, shown by the equation below. Which statement is correct? A. Nitric acid acts as a base. B. Nitric acid acts as a catalyst. C. Nitric acid acts as an electrophile. Or D. Nitric acid acts as a reducing agent. Let's start by identifying the type of mechanism that nitration of benzene is. So it's electrophilic substitution. So this should help us put some context to some of the statements. If we look at one by one and we start with A, well, we're saying that nitric acid is a base. And a base is a proton acceptor. So that means it's going to produce a positive ion when it reacts with an acid. And that's exactly what nitric acid is doing here. It's producing NO2+, which means that nitric acid is the base and sulfuric acid is the acid. So A is correct, but we need to check the other three just to double check and make sure that we're definitely getting the correct answer. So looking at B, nitric acid is a catalyst. So here is where knowing the type of mechanism really comes in handy. Their final stage of electrophilic substitution is the reformation of the catalyst, and that's where you reform sulfuric acid. So it's not going to be nitric acid that's the catalyst, it's actually sulfuric acid. So we can correct this statement by writing H2SO4 is the catalyst, and that makes B incorrect. Finally, if we look at C, nitric acid is the electrophile. So this is where some people might trip up, because it's not nitric acid that's the electrophile, it's this ion here, it's this NO2+ that's the electrophile, rather than nitric acid, but it is formed from nitric acid reacting with sulfuric acid. But C is incorrect, and it's going to be NO2+ that's the electrophile. Finally, we look at nitric acid being the reducing agent. So if something is a reducing agent, that means that it's going to oxidize, and its oxidation number will increase. So if we look at nitric acid and we work out its oxidation states, so HNO3, well, oxygen has a -2 × 3 oxidation state, which is going to be -6 overall for O3. Hydrogen has a +1 oxidation state, which means that nitrogen will have a +5 oxidation state in nitric acid. Then if we look at its oxidation state in NO2+, well, oxygen has a -2 × 2 oxidation state, which is -4, and we want an overall positive charge, So nitrogen is going to have a +5 oxidation state. So here you can see that its oxidation state hasn't oxidized and it hasn't reduced. It's just stayed the same. But that means it can't be a reducing agent, because if it was a reducing agent, its oxidation state would increase to, let's say, +6 or +7, or even higher. So D can't be correct. That makes our answer definitely A, and to get the mark for this question, you need to circle the box that corresponds to A. Aqueous solutions of ammonia, ethylamine, and phenylamine are prepared. Each solution has the same concentration. Which is the correct order for the pH values of these solutions? A. Ammonia, ethylamine, and then phenylamine. B. Ammonia, phenylamine, and ethylamine. C. Ethylamine, ammonia, and then phenylamine. Or D. Ethylamine, phenylamine, and then ammonia. Let's start by drawing our three structures. So that's going to be ammonia, so NH3. I'm going to draw it with the hydrogens in the lone pair. Then we have ethylamine, so that's an ethyl group with an NH2 attached. And then phenylamine, so we have a benzene ring or a phenyl side chain, and then an NH2 group attached. So these are our three structures, and we're looking for the correct order of pH values. So they've got it as an increasing trend going this way. So that means that the one on the left is the most basic, and then the one on the right is the most acidic. So a base is a proton acceptor. So that's what we need to keep in mind when answering this question, is which one will be the easiest to accept a proton. So looking at ammonia. Ammonia is the one in the middle because it's not got any side chains, it's got easily accessible lone pairs, and it can easily accept a proton. But we have kind of two opposites either side. We have ethylamine, which has an electron donating effect, which means it's very easy to accept a proton. And then we have phenylamine, which has a lone pair on the nitrogen, which is delocalized into the pi ring system, which makes it a lot harder to accept a proton. So that means that it's going to be the most acidic. So we're going to have phenylamine being the furthest on the right. So it's either A or C. But then we also needed to think about how easy it is for ethylamine to accept a proton because of its electron donating effect. And so that means it's going to be the most basic. So it's going to be the furthest on the left. And then ammonia's in the middle. So our answer is C. And to get the mark for this question, you need to circle the box that corresponds to C. Which element forms an ionic oxide that reacts with strong alkalis? A. Aluminium, B. Magnesium, C. Sodium, or D. Sulfur. So there are some key words in this question. Our first key word is that we're forming an ionic oxide. So we're looking for an ionic compound. And if we write the oxides of aluminium, magnesium, sodium, and sulfur, we get Al2O3, MgO, Na2O, and SO2. But sulfur is a non-metal, and to form an ionic compound you need a metal and a non-metal. Oxygen is also a non-metal, so a non-metal and a non-metal is actually a covalent compound. So our answer definitely can't be D because it's not ionic. Then the next key word in this question is that we want a strong alkali. So that means we're looking for something acidic. And there is a general trend of acidity from aluminium oxide to sodium oxide. And that's that sodium oxide is the most basic or the most alkaline, and aluminium oxide is the most acidic. So that means it's going to react the best with an alkali in a neutralization reaction. So the answer to this question is A, and to get the mark for this question you need to circle the box that corresponds to A. Which statement is correct about this reaction? A. The coordination number of cobalt decreases. B. The enthalpy change is large and positive. C. The entropy change is large and positive. Or D. The shape of the complex changes from octahedral. Let's work through these statements one at a time. So the coordination number of cobalt decreases. So we need to work out the coordination number of cobalt in its first state and then its second state, or its two complexes. So cobalt in its first complex has a coordination number of 6 because we have 6 ligands coordinating around cobalt's central metal ion. Then if we look at its second complex, we also have a coordination number of 6. And that's because we have 3 bidentate ligands, which means that each ligand is going to connect to cobalt at 2 points, and we've got 3 of them, and 2 times 3 is 6. So the coordination number actually stays the same, and that means that A is incorrect. And this also helps us with D. So it's saying that the shape of the complex changes from octahedral. But if you have a coordination number of 6, that means you're going to be octahedral in both complexes. So this stays the same also. So we're between B and C now. And the only difference between B and C is that one is looking at enthalpy change and one is looking at entropy change. To help us understand this, we need to look at what we're changing in this reaction other than our complexes. So we're going from 3 ethyl diamines to 6 ammonias. And that is a change in state from a liquid to a gas. And this means our system is getting more disordered, so entropy is going to be positive. And we're going from 3 liquids to 6 gases. So this is a very big, large, positive entropy change, which makes C correct. And so to get the mark for this question, you need to circle the box that corresponds to C. Which complex exists as optical isomers? And we're given 4 different possibilities. So the key in this question is that we're looking for optical isomers. And we can only get these with tetrahedral and octahedral complexes. So that immediately eliminates A, because this isn't tetrahedral or octahedral. You've only got 2 ligands, and for it to be tetrahedral you need 4 points where it bonds to the metal ion, and for it to be octahedral you need 6, and so it can't be A. Then we're looking at B, C and D. All 3 of these are octahedral, and that's because in B you have a bidentate ligand, and you've got 3 of them, so you've got 2 times 3 points of contact, which is 6, so octahedral. C, you have EDTA, which is a hexadentate ligand, so you've got 6 points again, making it octahedral. And then D, you have 4 ammonias and 2 waters, so 6, so octahedral. But then we're looking for optical isomers, and if we take a closer look at D, well, you can either get a cis or a trans arrangement of D, and if you did the mirror image you would still get cis and trans. So let's draw this out. So here I've drawn out the 2 different arrangements for D, and we have the trans configuration and the cis configuration. But if you did do the mirror image, you can see how the cis would remain cis and the trans would remain trans in terms of the configurations. So our answer can't be D because it won't have optical isomers, it just has cis and trans isomers. But both B and C can form optical isomers. So to get the mark for this question, you need to circle the box corresponding to B and the box corresponding to C, because these are normal octahedral complexes which when you reflect them, you get an opposite orientation and you get this optical isomerism happening. How many structural isomers with the molecular formula C5H10O react with Tollens reagent? A, 3, B, 4, C, 5 or D, 6? So Tollens reagent is the chemical test for an aldehyde functional group. So in our structural isomers, we're looking for an aldehyde. So let's draw the structural isomers of C5H10O. So we can start with pentanal, and that's got its aldehyde group on the end. Then we have 2-pentanone, so we have a ketone group on carbon number 2. Then we have 3-pentanone, so our ketone group on carbon number 3. Then we have 3-methyl-butanal, so we have a methyl group on carbon number 3. And then we have 3-methyl-butantuone, so we have our ketone on carbon number 2 and our methyl group on carbon number 3. Then we have 2,2-dimethylpropanol, so we have 2 methyl groups on carbon number 2. And finally, we have 2-methyl-butanol, so a methyl group on carbon number 2. Then we need to look for our aldehydes. So we have 1, 2, 3, 4 aldehydes out of our structural isomers. So that means our answer is B. And to get the mark for this question, you need to circle the box that corresponds to B. Which ion cannot catalyse the reaction between iodide and peroxide disulfate? Use the data below to help you answer this question. A. Cobalt 2+, B. Chromium 2+, C. Iron 2+, or D. Iron 3+. So let's look at the different equations we would get if we used each as a catalyst. So looking at the two equations that are the most important, and that's the reaction between iodide and peroxide disulfate. So if we start with cobalt 2+, well, that's going to give us the first equation of S2O8 2- plus 2CO2 plus, and it will produce 2SO4 2- plus 2CO3 plus. And that's because the reaction with peroxide disulfate is a lot more positive than cobalt's cell potential. So that's why the cobalt equation, or half equation, is flipped. And then if we look at when it reacts with iodine, or iodide, we get 2CO3 plus 2I minus, and that produces I2 plus 2CO2 plus. And that's because the cobalt half equation is more positive than the iodide half equation. So that's why the iodide half equation is flipped. But you can see in both cases how this is catalyzing the reaction. So cobalt is a good one, and it's not answering the question though, because we're asked which cannot catalyze. So we can eliminate A as one of our possibilities. Then if we look at chromium, so the half equations that we will use is the bottom one here. It's minus 0.41. And the equations that we get is S2O8 2- plus 2Cr2 plus, and that's going to produce 2SO4 2- plus 2Cr3 plus. So far, so good. Now let's look at the iodine equation. Well, it's actually more negative than the iodine half equation cell potential. So that means that the iodine equation will stay the same, and we'll start with I2, and the chromium half equation will flip. So then we get 2Cr2 plus, and that's going to produce 2I minus plus 2Cr3 plus. So this hasn't catalyzed the reaction with iodide ions. So B could be a potential answer. Therefore, we need to continue and double check that B is our answer. So moving on and looking at iron. Well, we get two equations. We start with S2O8 2-, and then we're adding 2Fe2 plus and producing 2SO4 2- and 2Fe3 plus. So we've used iron 2 plus to catalyze this first reaction. And then if we look at the iodide reaction, we get 2Fe3 plus 2I minus, and that produces I2 plus 2Fe2 plus. So here we've used the ion 3 plus to catalyse the iodide reaction. So we've used both of these to catalyse the reaction, which means we can't have these as our answer. And that means our answer is definitely B. So to get the mark for this question, you need to circle the box corresponding to B. Also, the reason that we've multiplied some of the equations by 2 is just so that the number of electrons matches. So with our metals, we have 1 electron in their half equation, but with iodide and peroxy disulfate, we have 2 electrons, which is why we needed to times by 2. Which species has a shape that is influenced by the presence of 1 or more lone pairs of electrons around the central atom? A. AlCl3, B. ClF3, C. IF6+, or D. PCl6-. Let's start by drawing each of our structures. So aluminium chloride has Al and then 3 bonds to chlorine. It doesn't have any lone pairs because aluminium has 3 electrons in its outermost shell and so can form 3 covalent bonds with chlorine very easily. So it's not A because we're looking for something that has 1 or more lone pairs that's influencing its shape. The shape of aluminium chloride is called a trigonal planar shape, and that is when you have 3 bonding pairs and no lone pairs. So then moving on to ClF3. So that's our central atom of chlorine, and then we have 3 fluorine bonds. So chlorine does have 2 sets of lone pairs in its shape, and this shape is a T-shaped molecule. So you can see that it's got 2 pairs of electrons, and that means that our answer is going to involve B, because these lone pairs are repelling and they're pushing the fluorine bonds down. Then if we look at C and D, well, they have the same shape, and it's called an octahedral shape. So if we do IF6, so we have this 3D octahedral shape where we have a fluorine bonded to each of these 6 points, and then we need to remember that we have our brackets and a positive charge. But there aren't any lone pairs in the iodine. It can very easily form 6 bonds with fluorine and have a positive charge. So no lone pairs involved here, so our answer is not C. Then if we do PCl6, so again we need this 3D octahedral shape, and then we have chlorine bonded at each of these 6 points. And we need our negative charge here. So both of these are called octahedral shapes, and they don't have any lone pairs, so they've got 6 bonding pairs and no lone pairs, which is not influencing its shape, so it's not going to be an answer for this question. That means our answer is definitely just B, and to get the mark for this question you need to circle the box corresponding to B. Some 1.0 moles per decimeter cubed solutions were mixed using equal volumes of each solution. Which pair of solutions would give the greatest mass of solid? A. Barium hydroxide and magnesium chloride. B. Barium hydroxide and magnesium sulfate. C. Barium hydroxide and sodium chloride. Or D. Barium hydroxide and sodium sulfate. In this question, we're looking for the greatest mass of solid, which means we're looking for an insoluble solid. And that's going to be barium sulfate. So there are 2 equations that form barium sulfate, and that's B and D. So A and C both form barium chloride, which is soluble in water. So these aren't our answers because we won't form a mass. We'll form an aqueous solution instead. So then let's write the equations. So we're going to produce for B magnesium hydroxide, so MgOH2, and barium sulfate. And then for D, we're going to produce sodium hydroxide, so NaOH, and barium sulfate, but we're going to produce 2 sodium hydroxides because we need to balance the equation. And this 2 means that we actually form a third barium sulfate and 2/3 sodium hydroxide because we're using equal volumes of each solution. Whereas in B, we have half and half. So that means we're producing more barium sulfate. And so B is our answer for this question. And to get the mark for this question, you need to circle the box that corresponds to B. Which indicator should be used in a titration to find the concentration of a solution of methylamine using 0.01 moles per decimeter cubed hydrochloric acid? A. Thymol blue with a pH range of 1.2 to 2.8. B. Bromophenol blue with a pH range of 3.0 to 4.6. C. Phenol red with a pH range of 6.8 to 8.4. Or D. Phenolphthalein with a pH range of 8.3 to 10.0. In this question, we're reacting methylamine, which is a weak base or a weak alkali, with hydrochloric acid. And hydrochloric acid is a very strong acid. So that means when we react these together, our equivalence point is going to be in the acidic region. And our equivalence point is what we want to test with this indicator. So we're looking for something in the acidic region. So that already rules out C and D as possible answers because they're in the basic or the alkaline region. And now we've got thymol blue versus bromophenol blue. And we have a very strong pH range versus a medium pH range for the acid. And we are reacting with a base still. So that means it won't be very strongly acidic, but it will be a sort of medium acidic equivalence pH range. So that means our answer is going to be B. And to get the mark for this question, you need to circle the box that corresponds with B. Lattice enthalpy values can be obtained from Born-Haber cycles and by calculations based on a perfect ionic model. Which compound shows the greatest percentage difference between these two values? A. CSF, B. CSI, C. LIF, or D. LII? In this question, we're looking for the compound with the most covalent character. So let's first look at cesium versus lithium. Well, cesium is larger and it has a larger atomic radius, which means it's going to be less covalent in character and more ionic. So we can eliminate A and B and just look at C and D. So now we're looking at the difference between fluorine and iodine. Well, fluorine is smaller, and that means it's going to have a smaller electron cloud, whereas Li with the iodine has a large covalent character because the lithium plus ion is very small and the iodide ion is very large, which means the lithium ion is going to draw electron density from the iodide ion, so it's going to be more covalent in character. Whereas because the fluorine electron cloud is a lot smaller, it's not going to draw as much electron density from the fluorine, so it's less covalent in nature, which means that lithium iodide is going to have the greatest percentage difference between the two values because it's the most covalent in character. So we can just jot this down as closure for this question. To get the mark for this question, you need to circle the box that corresponds to D. For this reaction at equilibrium, which combination of temperature and pressure would give the greatest equilibrium yield of products? A. High pressure and high temperature. B. High pressure and low temperature. C. Low pressure and high temperature. Or D. Low pressure and low temperature. So in this question, we're looking at temperature and pressure, which means we need to look at delta H and then the number of gaseous moles. So on the left, or the reactant side, we have 2 gaseous moles, but on the product side, we have 3 gaseous moles. So that means we want to move or shift the equilibrium position to favour the side with more gaseous moles, which means we need a low pressure. So we're looking at C or D. Now we need to look at delta H. Well, because it's positive, that means it's endothermic. So if it's endothermic, we want to shift the equilibrium position in the endothermic direction, because this is meaning that the forwards reaction is endothermic and therefore the products. So that means we want to increase the temperature. So we want a high temperature, and that means our answer is going to be C. So to get the mark for this question, you need to circle the box corresponding to C.